In this video, I'm going to show you about energy levels and quantized energy. I think first it's important to just talk about this whole idea about quantum mechanics. People use this word to invoke some sort of mystery to something, and like, oh, it's quantum mechanics, it's really tough. I mean, yes, understanding it's a little bit weird, but the basic idea of it is really pretty simple. If something is quantized, it just means something comes in certain amounts. For example, students in a class are quantized because they only come in, discrete amounts. 1, 2, 3, 4, whatever, 5 students. You can't have like half of a student. Well, I guess you can. It's sort of messy. But I mean, if you want to consider quantized things, it's just things that come in certain countable amounts. So for example, what we find out is that energy of a photon is quantized, which means the energy of one little piece of light, basically, that comes in only certain amounts. So this is actually something that's really important here. Oh, by the way, I put this picture right here of quantum mechanics because it reminded me of, it's almost like it's a pun, obviously. It's like a mechanic who's working on an atom. It's like the broken atom, so they're trying to work on it like it's a car. But let's talk about energy levels. So what we have is this process. This actually happens in your own classroom, perhaps, where you're sitting, where, if you look up and you have fluorescent light there, some sort of fluorescent light, what's happening is you're applying a potential difference to some atoms in a gas usually, and those atoms, the electrons in those atoms get excited. And when they get excited, they go up in energy level, just like what I'm going to be showing you here. And every time an electron goes up in energy level, that means eventually it'll probably come down. And if it comes down in energy level, this is the key thing, when it goes back down, it emits a photon, which is one piece of light, and it's got a very specific energy. This is the whole thing, is that energy is equal to HF. So I think it would help maybe if I just define this. So E is the energy, and this could be in electron volts or it could be in joules. H is just a constant. You can actually look it up. It's called Planck's constant, even though it's named H. And it's 6.63 times 10 to the minus 34. And then we've got, let's see here, frequency, which is measured in hertz, or 1/seconds. So this is the whole idea here, is the very fact that specific energy levels are possible, that means that specific photon energies are possible. And what I'll explain to you is this. See, this is actually coming from the Bohr theory of the atom, that there's only certain orbits that are possible. And so what you can look at is this. You can look at these different energy levels. It means that not everything is possible. This electron cannot be somewhere in the middle. It basically starts off, it's basically way up high, and then it has to drop down and then drop down and then drop down. So it can't just do something halfway. It's either right here, or it's the next one, or it's the next one down. It can't be anywhere in the middle. So let's say, for example, we have an electron, gets excited, and don't worry too much about negatives as far as energy levels go. Don't worry about that. That's just a weird thing about, you have to have the infinitieth orbit that gives you an energy of 0. So let's just assume, something goes up like this right here. What'll happen is, when it drops down in energy, which will invariably happen, so let's just say it drops down, let's say, to this one. Every time it does that little drop, anytime a photon goes down in energy, it's going to emit a photon. And that photon will have a very specific energy. Do you see, if you can figure out what's that energy difference here, what's this delta E here, what's that energy difference? That is going to be equal to HF, where H is that constant, and F is the frequency of the light. So essentially it tells you the color of the light. So what's really important is this, the very fact that there's different energy levels possible, that means that there's specific photon energies possible. And this is why we say this is quantized. We say it's quantized because the energy only comes in countable amounts. Look, right? The energy comes in 1 times F, or 1 times H, or 2 times H, or whatever. So it's always a multiple of H. So for example, this one right here, it'll also have another transition possible. Maybe it from there drops down to here, and then it drops down. Or maybe it goes all the way down in one go. You can see how these are all different photons. Each of these photons, you see the energy difference, the energy from the bottom to the top is different. Because of that, it'll have a different color. This explains why in your own, let's say if there's a fluorescent light above you, that explains why there's only specific colors. You know, you could take that light, for example, put it into a spectrum, so put it through like a prism or a diffraction grating or something, and actually break it up into its component parts. You'd end up seeing what that light was made of, because there's only going to be specific wavelengths possible, right? Because there's only these certain amount of transitions. In this case, I've drawn this as 1, 2, 3. There should be 4 different photons that I can see. That means there's going to be 4 different individual frequencies or wavelengths that you can see, right? Because frequency is just like wavelength. So I think that is something really, really important about quantum mechanics, is that things can be quantized. In this case, energy is. Energy comes in countable amounts or multiples of this magical number h. So now I've got an example for you. So we have electrons in an atom, and in this case right here, I think I chose, yeah, that looks like the energy levels for hydrogen. So we have electrons in a hydrogen atom, and they're excited. What I mean by that means they go up in energy level. And they have the following energy levels possible. So they tell you this in electron volts. First of all, how many different photons are possible? So what that means, I think it's maybe a good idea to try to just count them. So from here, how many different ways are there to go down in some way? What I like to do is be methodical. From here, you can go all the way down. You could go down by 2 or down by 1. Then once you're here, you could go down by 2 or down by 1. And once you're down here, you can only go this one. So it turns out these are all the different transitions possible. How many are there? There's 1, 2, 3, 4, 5, 6. So the answer here is 6. You see? So that just tells us there's going to be 6 different photons going on here. Now, what's the smallest wavelength of a photon that could be emitted? Now, you got to think a little bit about wavelength here. What letter is that? Do you remember? It's lambda. Now, the only equation we have to work with is E equals hf. So tell me about this. How is lambda related to f? Do you remember this? We have an equation, C equals f lambda, that tells us the speed of light is equal to the frequency of the light times the wavelength. So if I wanted to get wavelength by itself, what would I do then? Well, actually, no, let's maybe take a look at this. Yeah, it'll be okay. So E equals h, and instead of f, what can I do? I can say f equals, in this case, c over lambda. Because in this case, can you see, I can just get f by itself, so I divide the c by lambda, so there we go. And that means every time I see an f, I can replace it with c over lambda. In this case, it's supposed to be hf, it's going to be hc over lambda. So what this tells us in a way is this. We have this equation, or we have this equation. If we want the smallest wavelength, I just want to talk to you about it a little bit qualitatively. So smallest lambda. Do you notice, by the way, the frequency and the wavelengths kind of work opposites? Like a large frequency is going to be a small wavelength. And if you remember this idea, this is really going to help here. Because the smallest lambda is going to correspond to the largest. We want the largest frequency. Smallest lambda is largest frequency. And since E equals hf, does it make sense? If we want the largest frequency, then we want the largest energy. This is going to be the important thing. So we want the largest energy then. Does that make sense how we figured that out? So again, we want the smallest wavelength. And if we remember that wavelength and frequency are kind of opposites, in that, if one goes down, the other goes up, then smallest wavelength means largest frequency. And because energy is directly proportional to the frequency, that means that largest frequency will be the largest energy. So then take a look at these different photons here. Which one is the largest energy difference? I hope it's clear. It's from here to here. It's this one right here. This is my magical one that's going to help, right? That's the largest energy difference. So then let's maybe find the energy difference. Well, it's going to be minus 0.85. Minus, what is that, minus 13.6. What does that give me? That's 12.75. Yeah. Technically it's a negative, but the idea is we just want the absolute value of it. So we can say it's this many. Of course, it's electron volts. Now, this is great because now I have an energy. But maybe it helps to convert it from electron volts to actual real units that I can use. So do you remember the conversion factor for electron volts? I want to put EV on the bottom so I cancel them out. I need to know something per EV. And it turns out I know that 1.6 times 10 to the minus 19 joules is 1 EV. If you don't remember how to do that, remember, just that's 1 times the charge of an electron, which is 1.6 times 10 to the minus 19 coulombs. Multiply that by 1 volt, and it turns out a coulomb volt equals a joule. So I've just shown you again the derivation for what 1 EV is. So just so you know, you use that right here. So then I take my 12.75, let's see here, 12.75 0.75. I multiply that by the charge of an electron, because that tells me how many joules are in an EV, and I end up with my delta energy is 2.04 times 10 to the minus 18 joules. Why do I use this? This is because now what I can do, I can actually find now the wavelength. That's because I can use this equation E equals hc over lambda. So I know that this thing here equals hc over lambda. Therefore, I know that lambda equals h, which is going to be 6.63 times 10 to the minus 34. You just look that up. Times c, which is the speed of light, 3 times 10 to the 8 meters per second. I divide that by my delta E in joules, so that's going to be 2.04 times 10 to the minus 18. And let's see what we get. 6.63 times c. Divide that by 2.04 times 10 to the minus 18. And I get a value of 9.75 times 10 to the minus 8 meters. So if I want to do it to two significant figures, that would be 9.8 times 10 to the minus 8 meters. Or if you really want, you could say it's 98 nanometers, I guess you could say. So but they're both okay. You could say this one, or you can say it's 98 nanometers. Basically, it tells you it's really small. Remember, if you think about what we can see, the human eye, we can only see things around 400-ish nanometers. That's what we can detect. So you probably wouldn't be able to detect this with your human eye, but you could use some other detectors to detect this. So we can use devices to help us with this. So do you see how this quantum mechanics kind of works? The fact that these energy levels, there's only certain ones possible, that's what leads to the fact that only certain photon energies are possible. So that's why the energy of a photon, E equals hf, is quantized, because it's always a multiple of this magical h value. So see, quantum mechanics doesn't have to be so hard.